Yeah, my name's Philip Cardiff, and you may have seen my presentation this morning. So I'm an assistant professor in University College Dublin in Ireland. In this session, I'm going to go through this Solids4foam toolbox and give you an idea of how to use it, basically an introduction to it. Just once again, in case you didn't hear before, though it's been advertised a couple of times, I'm the current chair of the OpenFOAM workshop committee, and I'm organizing the next OpenFOAM workshop, which will be in June. It was meant to be in Dublin, but unfortunately it will now be online, but it looks like it'll be a really interesting event. So we already have almost 140 abstracts submitted for technical talks. That deadline closed on the weekend, but I've opened it again in the abstract submission link, just in case anybody from this event still wants to submit. You can still submit a one-page or two-page abstract. And that's just a standard disclaimer. So the structure of these slides, there's 5 main things I'm going to cover. So the first one is installing this Solids4foam, and then I'm going to give an overview of what is this Solids4foam toolbox. I've prepared 2 tutorial cases, so I won't go through both of them. So previously I've given similar trainings to this. So previously I've talked about this hot sphere tutorial. So just for a change, we're going to go through this perforated case. That's going to be perforated plate case. Then after that, we'll look at a cylinder in a channel. So depending on the time, we might skip over that. So the 3 here is a solid analysis, 4 is a fluid analysis, and then 5 is a fluid-solid interaction analysis. So previously I've looked at this beam and cross flow, but I've added another one here called flexible dam break, which might be more interesting, just a change for me. So we might do that one instead. So the approach I'm going to take in this training is I'm going to jump between the slides and the terminal and power view. So try and make it hands-on from my perspective. I'm not sure if it'll be possible for you to follow along, but if you do have access to Solids4foam, then you may be able to. So there's 2 ways to install Solids4foam, or at least 2 ways. So one is natively. So if you have a version of OpenFOAM installed, you can download this toolbox via Git. And then if OpenFOAM is sourced, if you just run the included all wmake script, it should build. Alternatively, you can use Docker. And I'm just going to talk a little bit about both of those, just briefly at the start. So natively, Solids4foam compiles with foam extend 4.0, 4.1, and OpenFOAM v1812, v1912, and v7. One comment is the tutorials will all run out of the box with foam extend 4.0 and 4.1, but for 1812, 1912, and 7, the tutorials won't run out of the box. There's a number of manual changes you would need to make. I'm in the process of automating that, so it'll automatically make those changes, but it's not complete yet. So if you want to have an easy life, just run the 4.0 version. Also, I've noticed some issues with foam extend 4.1, so I recommend sticking with 4.0. So if you go to this Bitbucket address, /Phil Cardiff, Solids4foam-release, you can clone the latest repository using these commands. So you'll have access to these slides afterwards, and I think, Daniela, you said you put it in the chat anyway. So people in the chat, let me open the chat. Yeah, so the link is in the chat if you want to download these slides, so you can copy and paste out those commands. So after you download it, you'll have a folder called Solids4foam-release if you didn't give a name to the Git, or you can rename that to whatever you want. Inside that, there's an all wmake script. So once you've one of those versions of OpenFOAM sourced, if you just run this script, it will compile Solids4foam. So it should take only 5 or 10 minutes. And once that script finishes, if you run Solids4foam-help, you should get the typical solver error being printed out, knowing that it is installed. So I do have an automated compilation process set up, checking that the master branch does compile on all these. So it does compile on clean versions of all of those. So it should compile without any errors. And installing Solids4foam via Docker. So what is Docker? Docker, if you haven't heard of it, is basically like a lightweight virtual machine or something like that. So I use Mac by default. So if I want to use OpenFOAM on my Mac, I can either natively compile it, which isn't for the faint-hearted, or I could install a virtual box or virtual machine, which is a bit of a pain. So Docker is a really nice, quick, easy way to do that. So Docker lets you run essentially like a light version of Ubuntu with OpenFOAM directly on Mac or Windows. So I publish on my Docker Hub, I publish different versions of Solids4foam. So there's the default one with foam extend, but you maybe, I need to check, but I think you can find different versions of Solids4foam as well, but at least the foam extend version is there anyway. So if you have Docker installed on your Mac, Linux, or Windows, you can just run docker pull, and that will pull down a fully working version of foam extend 4.0 and Solids4foam. And you can see it's based on Ubuntu 18.04. Then you can run that using these commands here, and you can set up shared folders and things like that. If you're familiar with Docker, you'd be familiar with this. And then once you log into that Docker container, you can check Solids4foam works. Everything's fine. And then just to mention, I think the password is removed from the sudo account in that Docker container, so you can easily install Emacs or whatever editor you want to use or any other software. Okay. So just an overview of Solids4foam before I open up the terminal. So what's the idea behind it and what's the motivation for it? So the main motivation came initially from fluid-solid interaction. So it's fluid-solid interaction, you want to couple some fluid solver like piezo foam with some solid mechanics procedure, so like solid displacement foam. So if you want to do that, let's say the traditional OpenFOAM approach would be make a new solver called piezo solid displacement FSI foam or something like that. And there are solvers like that. I know I shared one called ICO FSI nonlinear elastic something. Or there was FSI foam in a few different versions. So they have a hard-coded version of the fluid solver and hard-coded version of a solid mechanics solver. So if I want to make a new solver using a compressible fluid formulation, I actually have to copy a lot of code and make an entirely different solver. So code repetition and copying is bad from a software design perspective because it allows many opportunities to introduce bugs. And also if you fix a bug in one version of the solver, it doesn't automatically fix it in the other version. So the idea here was, and this is taken from the Extend Bazaar, was the first toolbox doing this, was to have a class for the fluid solvers and a class for the solid solvers, and then you can just have one solver, in this case Solids4foam, and then depending on your runtime settings in your case, you can decide whether you want to call ICOFOAM or ICOFluid or ICOFOAM or piezofoam or simple foam or row central foam or whatever. And in the same way with the solid, there's many different types of solid solvers, and you can decide which one to pick. Also for the coupling in between, you could pick some runtime selectable coupling procedure. So for example, like the fluid model, the way we've named them, instead of piezofoam, we just call it fluid. So that's piezofluid class. So that just it's basically copy and paste the piezofoam code into a class. So we can just call a function solve, or we call it evolve. And in the same way for the solid models, just like in fluid mechanics, you can have compressible, incompressible formulations, steady state, many different approaches, semi-compressible. You can have the same thing in solid mechanics. So the two principal categories are linear geometry and non-linear geometry approaches. So that's small deformations or large deformations. And then within that, you can have different types of approaches as well. So each one of those are implemented as a class. In fluid mechanics, the critical thing for getting the stresses accurately predicted is often the turbulence model. And the constitutive model in solid mechanics fulfills the same role. So if you want to accurately predict the stresses for your given physical problem, you need to pick an appropriate constitutive law, or mechanical law we call it. So linear elasticity being the most simple one, but you might have some plasticity, the pore elasticity, viscoelasticity, and something else. So for example, commercial softwares like Abacus and ANSYS often let you write a user subroutine to define your own specific one. And it is possible to couple in one of those Fortran procedures with Solids4foam as well. One question, or two questions. Is Solids4foam the solid core of OpenFOAM's FSI capabilities? And that is a good question, and it's probably a subjective question. So Solids4foam is essentially an outlet for a lot of the code I've worked on, along with many collaborators. Predominantly, he's Željko Čuković, and he's a professor in Zagreb. He spent a lot of time in Dublin as well, and I continue to collaborate closely with him. And also, there's been many different PhDs in this area, and I've tried to collect a lot of that code and share it just to make it accessible. Initially, it's for internally for a new PhD student when they start. I can say, here's some code from that was previously used, but then we made it public, and some people seem to find it useful. But this is not the only way to do FSI. There are many people working on FSI in OpenFOAM. So this is just one toolbox, and by all means, I recommend looking at what other capabilities are out there, and there may be better ways to do certain things. And also, can Solids4foam work with anisotropic structures like composites? So there are anisotropic constitutive laws available. There are some, available. So you would specify the material orientations or directions. One thing with composites, because I have some experience working with composites myself, there are many different approaches to modeling composites. So let's say if you're at the macro scale, if you just want to capture the principal directions of your laminates and without caring about the plies, then yeah, that's probably fine with some of the available tools. If you really want to specify the individual plies and their directions, I know, for example, Abacus has like a composite layup tool that lets you define all of that and calculates the equivalent properties. So that's not available, but in theory, you could implement it if you really wanted it. And then we have the coupling procedure, fluid solid interface, we call it. So we've we've a couple of different methods implemented. So this IQNILS stands for inverse quasi-Newton thinking complete or inverse least squares. So this is probably the state-of-the-art method in literature, and from talking to the original author of it, and also talking to guys in the Precise toolbox, which is a coupling toolbox. However, based on experience, this particular implementation may not give the same behavior as, for example, Precise. So I've seen some comparisons where the Precise implementation is a bit better. But because this is open, we have opportunity to look at the code and figure out how to fix it. But these are the coupling procedures implemented. Okay, I said there's my first solid case called hot sphere. So rather than going through this one, which was this problem, I think I showed it in the presentation this morning. It's this pressurized sphere, and it's a thermomechanical problem. So instead, I'm going to skip over that, and I'm going to go to my second solid case. So I still hold your hand as we go through it. And in fact, that should say V. I'll edit as we go. And called perforated plate. So I will, as we go through this, I'll jump in between the terminal and my slides. So this is a pretty chock-a-block slide, but this is basically the problem definition. So the problem is we have a 2D plate. Where's my mouse going? Here it is. We have a 2D plate which has a hole in it. In solid mechanics, plates with holes often come up as benchmark or classical test cases because they're simple, but they're interesting. So it's a plate with a hole, but the difference from the classical problem is we have an elastoplastic material. So that means the plate can elastically deform like an ideal solid, which lets it spring back, but also once the stress gets to a critical value, permanent deformations will occur. And we're going to assume small strains, and we're going to ignore inertia and gravity. So our governing equation is just the sum of surface forces equals 0 for each cell. This is the constitutive law, J2 means plasticity, but this slide really is for reference. It's not a great slide for presenting. And on the boundary conditions, we're going to apply a time-varying traction. So we're going to increase the traction up until 10 seconds and then decrease it back to 0 from 10 to 20 seconds. So we're going to pull it and then release it again to let it relax. And we're going to apply a large enough traction to cause permanent deformation and then let it relax again, and then we'll see that we'll be left with residual stresses, even when we don't apply any external stresses. This is the geometry itself, and this is the sort of mesh we're going to use. And for reference, I often use a number of other software. So Abacus is a commercial finite element software that's been around for 30 or more years. So I've ran this case in Abacus finite element, just check we get the same answer, everything's fine. And I've compared, for example, the displacement of the top point on the hole and for different meshes versus finite element, and the same for the final residual stresses, and everything makes sense. I have a question, can the plasticity due to a plate's own weight be modeled? Yes, so I've said we turned off gravity, but it's really easy to turn gravity back on in the case. So in this case, we can do that. I can't remember if this is steel or aluminium, but gravity would have to be pretty strong to plastically deform a plate, or it would have to be a very large plate. But yeah, we can do that, and we can see, we can play with that and see how it works. Okay, to be able to run this case, first thing to do is make sure you have a run directory. So if you've never used OpenFOAM before, make sure you have a run directory and change to it. And then I've assumed that Solids4foam has been downloaded in the parent directory of your run directory. So one directory up. So inside Solids4foam, there is a tutorials directory, and you can just copy all of that into your run directory, just so you don't make edits to the main Solids4foam tutorials themselves. Even though that's fine because it's downloaded with Git, so you can still recover everything. Then CD into the tutorials, solids, elastoplasticity, perforated plate, and then there's an all run case, an all run script. We'll run it and look at the results. And before I do that, the structure of the tutorials in Solids4foam, and there's 3 directories: fluid-solid interaction, fluids and solids. So hopefully it should be intuitive what is in each of those directories. And then the solids are not broken down by solver. Remember, there's only one solver, Solids4foam, but instead they're broken down by physical phenomena. So if we look at solids first, we have elastoplasticity, fracture, large strain elasticity, linear elasticity, multi-materials, pore elasticity, thermoelasticity, viscoelasticity. I think there are an infinite number of types of elasticity, but here are a few of them. I just have added notes on if you're using Docker, you have to be careful where you've placed your shared directory, and also opening PowerView. It won't directly open out of Docker, so I suggest installing PowerView on your physical computer, and then opening a second terminal on your physical computer where you navigate to the shared case. So if you put the case in the shared folder, then you can just see it from the main computer itself. Okay, so I'm going to jump over to the terminal now, and we can I can play through the case itself. So here's another question. Can a moving distributed load be modeled? So there are a number of boundary conditions available. Is there a moving distributed load? I'm not sure if one is implemented. I know you could use Groovy to modify one of the existing load boundary conditions, though it wouldn't be that difficult to write your own boundary condition. So if that is something to do that, it's not that difficult to do that. So you can always contact me afterwards, or we can do it by just posting on the forum, and we can discuss it there. But you could use Groovy. Groovy BC will let you do it as well. Okay, so let me jump over to the terminal. So first of all, is my text large enough to read? Hopefully it is. I'll assume it is, and if it's not, then maybe just post in the chat saying please make a video. So I've downloaded a fresh copy of Solids4foam just in case. So if I type ls, and then just to let you know, a lot of the commands I have an alias overwriting them. So ls for me is actually ls/all, because I like to see all the settings for my files and folders and permissions and things like that. So this is Solids4foam. When I go inside it, it's meant to follow the same structure as OpenFOAM. So it has applications, tutorials, SRC. There's some documentation as well in Markdown format if you want to look in there as well. Okay, so I'm going to go into tutorials. If I ls here, you can see solids, fluids, fluid-solid interaction. There's an all test function as well you can check. Go into solids, you can see all the different types. Go into elastoplasticity, and then we go into perforated plate. Okay, so if I open up all run, all it does is it runs block mesh and then Solids4foam. So if I run block mesh, Solids4foam, you'll see it runs through a number of time steps. Also, you can see it's printing out some information. So it's saying percentage of the cells in the material which are actively yielding. So you can see as the time increases, at some point plasticity kicks in. And I think this case takes about a minute to run. So remember, the load is increasing up until 10 seconds. So you can see now, as we get to 6 seconds, 1% of the cells are starting to permanently form. As we keep increasing, that's going up to 2%, 3%, 4%. It says 12 cells, 21 cells. And then the loading is removed, so you can see it goes to no more cells, possibly forming, and then the load is slowly ramping back down again. So I'm just going to pause that for a second, open Power View, and set that going again. Power View opens, we can have a look at it while that's still running. Okay, so press apply when it opens. I'll set it to 2D because it's a 2D case, and on the mesh, there we go. So you can see we have 15 time steps as of now. If I refresh it, you can see it's almost got to 20. There's going to be 20 time steps written. So if I look at some of the fields, so I might look at the sigma EQ. So sigma EQ is called the equivalent stress, which is also known as the von Mises stress. So stress is a tensor, and so the equivalent stress or the von Mises stress is a scalar stress, and it's some combination of the stress components, and it's normally a good indication of whether a material is going to permanently deform or not. So essentially, when the sigma equivalent reaches a critical value, which is called yield strength, then permanent deformation starts to occur. Okay, so if I play through this, let me just refresh. I think we should have all the time steps by now. Yep, so you can see the load keeps increasing. So if I just scale this based on the full time scale, so if I press play, the load increases till 10, and then it decreases again. But when we get to 20, even though there's no load applied, there are stresses, and that's because the region just here by the top of the plate, that has permanently elongated. So its natural stress-free length is greater than the surrounding material. So then when you let it relax again, you have a mismatch between the lengths, so you lock in some residual stresses. And so if we look at epsilon P equivalent, so this is the equivalent plastic strain. So you can see this is permanent deformation basically. So we can see it increases and then it just gets frozen in. So after 10 seconds, it's just frozen in. For reference, in case you don't know, if we have symmetry planes, you can use the reflect filter to see the full plate. So if I do that twice, reflect about the X main and the Y main, now we have our full plate. Also, by default, the deformation is very small here, but if you do want to see them, what you can do is use the warp by vector filter. So if you click that, use the displacement field D or point D, and press apply. If we play now, well, the deformation is pretty tiny. I'll just use point D. It's pretty tiny here, because the true displacement is only microns in size. So that's like less than a human hair. This plate is 20 millimeters. But we can rescale that just so we can see the deformation. So if I click auto scale, press apply, then that's actually too large. Maybe something like 200. Yeah, something like that. So this is basically Power View is just amplifying the deformation so we can see the kind of type of deformation present. So if I press apply now and play through, you can see, well, sort of, you can see there. Let me go back and turn on the plastic strain. I think 200 is still too big. We set to 100. And if I go to times up to 10, so you can see just at this point here, permanent deformation occurs in some of the cells. So if I play it again, you can see just now it sort of starts to neck there and you get some permanent deformation, and then that's locked in. A couple of other fields interesting to look at here. So D, which is the total displacement. DD is the increment of displacement. Maybe it's not very intuitively named. So that's the change in displacement from time step to time step. Underscore 0 just means old. D epsilon is the increment of strain, in this case P, which means plastic strain. A couple of other interesting ones, active yield. So this shows where material is in the current time step if material is undergoing permanent deformation. So if I skip to 6, you can see this material here has started to permanently deform. We go 7, 8, 9, 10, and then if we go to 11, So at 11, there's no cells undergoing further permanent deformation. So active yield isn't showing cells that have had any permanent deformation, it's just showing cells that are undergoing current plastic deformation. More question, hi Philip, understand the implicit dynamics cases such as forming, deforming can be solved using Solids4foam. Can explicit dynamics like blast case be solved using Solids4foam? So if you take so you can run an implicit method with very small time steps, and it will let you analyze dynamic problems. However, it would still be an implicit solution algorithm, so it may not be the most efficient way because each time step might be expensive to solve. Even though for a segregated solution algorithm or an iterative one, it may actually not be that expensive. So what about actual explicit methods? So like an FEA, finite element, they'll often use for like these class or crash or blast problems, you really use explicit finite element procedures. So most of the solid models are implicit in Solids4foam, but I've included some explicit ones. Most of them are example ones, just showing how explicit methods could be implemented. There is one I've copied in from Gibram Haider at Swansea from his PhD. He implemented a Godunov type upwinding Lagrangian fully explicit method, similar to how, let's say, row central foam would work. And that's fully explicit. So I ported that, but he, of course, has his original repository as well, where you can directly download it. So I can, if we have time at the end, I can look at some of those cases. But yeah, in principle, it can be. However, timescales is often a challenge. So the speed of sound in gases is often much lower than it is in solids. So the speed of sound in solids could be an order of magnitude higher. So you have to be careful then. Your time step may be limited by the current number in the solid, which is probably not what you want in your blast simulations. So maybe an implicit solid method actually is not a bad idea. I'm happy to chat further afterwards if you have particular cases you wanted to chat about. Okay, let's keep going. So these slides are meant to be partly for reference and partly for me to remind me what to look at. Or what to cover. So don't worry if I'm going a bit fast, because they're here for your reference as well to look back at. So if I just, before I start changing things in the case, like gravity, if I look at the structure of the perforated plate case, it's a normal OpenFOAM case. I have a zero directory constant on the system. In zero, I have the field I'm solving for. In this case, it's DD. So this particular solid model solves for the increment of displacement. So confusingly, D represents displacement and increment in Solids4foam. So anytime you see D in front of something, it probably means increment of something, unless it's D on its own. So DD means increment of displacement. So that's what the equations solve for. It could, in some of the solid models, they solve for D displacement. They could solve for velocity, could solve for velocity pressure. And in this case, the total displacement at any time is the old displacement plus the increment. Inside DD, inside this boundary condition, if I open it up, and I'll go back to the case for this. So you can see the dimensions are meters. It's a vector. I have some symmetry planes. Just for reference, the reason I'm using this special symmetry plane is it has skew correction. And recently I found out OpenFOAM symmetry planes actually have a skew corrected flag, a hidden one that you can enable that does the same thing, but that's all it's doing. So on the right-hand side of the plate, we have what's known as a solid traction condition. So this is like a force per unit area with line. Traction is like a stress vector. So this can take multiple different types of inputs. So it can take a constant traction, you just tell it the traction, or it can take a traction series, which is time versus traction. So if I open up that on the right-hand side here, so constant time versus traction, you can see it's just an XY table of time versus traction, and the values get interpolated between these. So from 0 to 10, it ramps up to this value in the X direction, and then it ramps back down to 0. But you could like generate this in Excel to make any curve and just paste in all the data points. Pressure here is surface pressure. It's not hydrostatic pressure. They're not the same thing. So this is the normal component of the traction vector. So just because your surface normals may not be all pointing in one direction, we have the option here to specify pressure, or you can specify a pressure series. So you could have a traction or traction series, pressure series. And down the symmetry plane, up is basically stress-free. So it's like open to the air basically. So I use solid traction again and just set the traction pressure to 0. And then the same with hull, and then I've empty front and back. And so these slides just describe that. And the all run directory, all clean, we looked at those. In this case, just block mesh and followed by Solids4foam. So the only differences between Solids4foam and the normal OpenFOAM solvers are the addition of a couple extra files. So one of those files is called physics properties. So when Solids4foam runs, it expects to find this physics property dictionary. And inside this physics property dictionary, we can specify is it a fluid analysis, a solid analysis, or a fluid-solid interaction analysis. So in this case, it's a solid. And if it's a solid analysis, it looks for solid properties. And inside solid properties, you specify the type of solid solver to use. Equivalently, if you set this to fluid, it'll look for fluid properties instead of solid properties. And it'll look for, do you want to use like an icofoam or a nitrofoam, or what type of solver do you want to use? And then finally, if you use fluid-solid interaction, we're going to do a tutorial to see what it'll look for. But it looks for FSI properties, and then it'll expect to find the fluid and solid region in the case. So I'm skipping quickly through the text here, but this is once again just for reference. So in solid properties, and I can jump back to my terminal quickly. There you go, Emacs constant solid properties. I've set the solid model here to what's known as linear geometry. And then it may have some settings, all of them default to reasonable values, but it's basically like tolerances for solving these solid equations. And that's about it. And then, for example, if you want to change to a large strain approach, we can use a large strain solver here, or there's a variety of different small strain approaches. In short, here we're using the linear geometry solid model, and that takes DD as its primitive variable. And the linear geometry approach is also known as a small strain or a small strain rotation approach. So it's assuming that the cell geometries, i.e. the faces and the cell areas, that they're independent of the displacement here. It's assuming that the displacement is so small that it doesn't change volume or areas. So this is a pretty standard assumption in stress analysis. So in the same way, let's say that incompressible CFD is the standard for CFD, small strain or linear geometry is the standard for stress analysis. So there are some special cases like metal forming where that's not okay, and you need to update the volumes and areas. And now we also need to specify the mechanical properties. So if I go here, so Emacs constant mechanical properties. You can see here I've set the type to linear elastic and use plastic. So if I set this to linear elastic and ran it, then I'd have no plasticity in the case. It would just be elastic and the stresses would go to 0 at the end of time 20. So I have to specify here the stiffness, the Young's modulus, the Poisson's ratio, and then I can give a file name which gives the yield strength or how the yield strength varies. Also, sometimes when there's plasticity, it can be useful to solve a pressure equation, a Poisson equation, to avoid oscillations. So you can optionally turn that on as well. The name here, aluminium, isn't really used. It's just for your reference, unless there's more than one material. If there's more than one material, then this name, it'll expect to find a cell zone in the mesh with that name. So if you have two materials, the way Solids4foam knows which cell is in which material is by cell zones. So for example, in block mesh, you could have two blocks, and one could be steel and one could be aluminium, and then Solids4foam would expect to find an aluminium material and a steel material. Okay, there's some extra things here to change, and we can play with those. So you can see there's a dynamic mesh dict, and by default, we're just using a static mesh here. And then also there's a gravity field. So that's one thing actually, and that was one of the questions, so let's see the effect of that. So I'm just going to remove the results, the previous results. And I'm gonna turn off the boundary condition. Where is it? So the right-hand boundary, I'm no longer going to apply a traction here. I'm just going to set it to be 0. So uniform 0, 0, 0. So I'm not applying any external load in surface loading. Instead, I'm just going to turn on gravity. So I'll set the value of gravity to be -10 meters per second. Also, I don't need to run it for loads of time steps. Now I'll just run it for one time step. So I'll set the end time to be 0.1, and I'll write the first time step out. So I go Solids4foam, run one time step. You can see no cells yielded. You can see the maximum stress is 800 pascals. And for reference, I think the yield stress in this case is 243 megapascals. So just in this case, gravity alone is a long way from true gravity is a long way from causing any permanent deformation. So I see there's no active yielding, but we can look at the stresses. Actually, it probably doesn't make sense to have the second symmetry plane here because gravity is acting down. So if we flip it, we'll have gravity acting towards the center plane. So in this case, if I just work this, just to see if you imagine this is just half a plate and gravity is applied, I'll rescale the deformation by a large amount. That's too large. 1E7 maybe. So that's too small. 1E7. Yeah, okay. So I'm really magnifying the displacement here, but gravity causes the whole thing to sag. But we can see, let's ramp up gravity to be a really large number. So we'll say for some reason we're on some other planet where gravity is, I don't know, 1 million times larger. I'll run Solids4foam again. And in this case, 63% of the cells yielded in the mesh are permanently deformed. So let's just have a look. And obviously the scaling is crazy here, so I need to fix that up. That's still too large, so maybe set 10. Okay, so if I look at active yield, so it's basically saying if I go from the first time step to the second, all these red regions have started to permanently form this time step. And if you look at that, the magnitude of that permanent deformation, you can see it's large around those regions. So if gravity was high enough, it could be causing permanent deformation in this case. Okay, let me keep on top of any questions. So thanks for the questions. Can rupture be modeled? And when can we get training materials? And please, is it possible to get all presentations posted? So for the second two questions, the link is in the chat. And I don't know if you join it late in Zoom, I don't know if you can see it. So I'll post it again. Oh, that is not what I meant to copy. Oh, I can't post the link. Maybe Daniela, if you're still listening, you can put the chat again.
No worries, I will do it now.
It's a good test that you're still listening. So good job, you passed. Okay, so if we keep going, so that's gravity. And let me see, just to comment on the residuals. The residuals are customized, so they're not written out in standard OpenFOAM format. So if we looked at the terminal, we saw it was printing out different types of residuals. So in this case, okay, let's see if I can just find my cursor. Okay, here's my cursor. So in this case, it prints out the correction. So these segregated solid models do a lot of outer correctors, so hundreds or even thousands of them. So you don't want to print all those out, so it just prints every 100 or something like that. So there's three types of residual here, a green, a red, and a purple. So there's res, which is like the initial residual printed by OpenFOAM. And rel-res is one that is calculated based on just the change of the displacement field. So it's good to check both of these. And then there's a material residual. So if we have plasticity in a step, then we want to make sure that which is a nonlinear process, that's also converged. So we check for all three of those things. And some other things I'm skipping through quickly here. These once again are for reference, these slides, so I won't have time to look at all of them. In terms of FE schemes, you can see you asked about dynamics, so let's just take a look at that. So I'm going to remove the results again. So, open up system FE schemes. Instead of having steady state, I will set them to Euler. So I'm going to re-enable the inertia term. I am going to make gravity, no, I'll leave gravity to be a large number. Our loading will come from this extreme gravity. And what I'm going to do is, because things will happen very quickly now, I'll look at a very short duration of time. So maybe 0.1 of a millisecond, so 100 microseconds. And then maybe I'll use a time step of one millisecond or something like that. So, and I'll write out all those time steps. So let's see what happens. Okay, a lot happened very quick. You can see that almost the entire domain is Lulu. But okay, it drops off again. It's probably going to start bouncing a bit now. Okay, I'll leave that running and I'll jump back here. Skip to the first time step. So now remember, we're only going a very small time. So it's like suddenly after 1 microsecond, gravity just gets turned on and the plate just will suddenly feel the weight of gravity. And you would expect it to start to bounce or something like that. So if we go sigma equivalent, turn that on, we scale it. I keep playing, you can see the whole plate starts to squash down. Keep going. Okay, so the deformation here is magnified, so this isn't the true deformation. So now 1 would be the true deformation. So you can see it starts to squash down, and then it starts to relax a little bit, and then it'll probably just continue to bounce forever. So eventually the bouncing will stop here just because it's using a first order time scheme, so that just deletes energy and it'll stop bouncing. But if you had a good time scheme, you would see it bouncing for a long time. Okay, how are we doing? So this is just a comment on using least squares versus Gauss linear. It's basically just always use least squares because the stresses are quite sensitive to the gradient scheme. And Gauss linear is generally not very good unless you have a very special formula. Okay, I'm going to skip over the code just in the interest of time, but I referenced the code itself, what Solids4foam, the solver looks like. So the top level solver is basically empty, it just calls a physics class below it. And then also I show how some of the solid models are implemented. I know I'm going very quickly through it here, but I just want to make sure I have time to get to the FSI case. And once again, I said these slides really are meant to be partly documentation. So I'm going to jump on to not my first fluid case because nobody cares about using Solids4foam for fluids. It's just an example. But I'm going to go to my first and second FSI cases. So we're going to go to my second FSI case. So it's called flexible dam break. So most of you will be already familiar with the dam break test case. So it looks something like this. Apologies for the resolution. But I've changed just to make this little dam here to be flexible, so it'll deform and the wave hits it. So when we run this tutorial, it'll look something like this. So I get this little plate will just bounce side to side as the liquid hits it. So just quickly going through the theory, basically FSI, you solve for the fluid equations and the solid equations, and then you have these extra conditions which must be satisfied. So the velocity of the fluid interface must be the same as the solid interface, like continuity of velocity, and the same with its displacement, and also continuity of force. So the force on the fluid side should be equal and opposite to the force on the solid side. There's many different FSI type procedures. Well, 2 predominant ones. Partition is the most common one, where you solve a fluid case and then you solve a solid case and you pass information between them. It can be done monolithically, and it has to some degree in OpenFOAM, but I would say those procedures would need some development to make them useful, generally useful. Okay, so if I jump into the case itself, just before I run it, let's just look at the differences between the solid case we just saw and this FSI case. So there's only one main difference. So we once again have physics properties, and that will be set to fluid-solid interaction. When that's set to FSI, we will need to give an FSI properties dict, which defines the coupling procedure. But then the Solids4foam will expect to find fluid and solid directories in 0, constant, and system. So your boundary conditions for solid will go in 0, solid. Your boundary conditions for the fluid will go in 0, fluid. And the same for your constant, your mesh and settings for the fluid and solid, and the system settings. So that's the only difference, is just using these region options. So if I just open up my terminal and I go back, we go into fluid solid interaction and I go flexible dam break. And if I open up all run, so basically all it's doing here is it's running block mesh for the solid, block mesh for fluid, and then it's running set fields to set the initial alpha field for interfoam. And that set fields doesn't have a dash region option, which is annoying, so I have to manually move around the files to set it, but that's all it's doing. So if I all run here, so I can leave that running, put it in the background, I'll open up PowerView. So a couple of other differences. So when I open up PowerView, if you've ever worked with multi-region cases, you'll see I have the fluid mesh and the solid mesh. So if I want to treat those differently, turn on different fields in each one, I can open the case foam file twice, or you can use filter extract block. So if you go filter extract block, then I can extract the fluid first, as applied. So this will be my fluid. And then I go back to the original case.foam and go filters, reasons, extract block, and solid, and that's applied. So if this is a linear geometry, a small strain solid solver, you need to use the warp function and warp the displacement field by 1 to see the true displacement. So can't remember, I think it takes a couple of minutes to run this case. Let me just turn on the alpha field, alpha 1. So press play, see how we're doing. So the water comes down, hits the little column. Oh, we're just at the point when it's hitting it. Refresh the time step, see if we get any further. Okay, so we can see I set this to 2D, and you can see it's hitting it. And in the solid, we have all our normal fields. In this case, it's elastic, but we could just change the mechanical properties to be elastoplastic, like in the perforated case place, and then we would see where permanent deformation occurs. So we look at our signal equivalent field or our displacement field, and we can play and see as it comes down, the water hits it. Also, you'll see the interface is not conformal, so the coupling procedure is interpolating between these using GGI or AMI, depending on which version of OpenFOAM you might use, or some other methods. So we can keep playing that, and then it'll run to the end. So let me just continue on through this. So you can see in the boundary conditions, in this case, it's like the interfoam boundary conditions will be in fluid, so velocity, dynamic pressure, alpha. Also, it's a moving mesh problem, so it's actually inter-diem foam. So you have to specify your moving mesh fields, boundary conditions. In constant, we look inside fluid. So inside fluid, you have your dynamic mesh dict. Fluid properties is the only thing you might not be familiar with. So that's defining to you. That's basically where you say use interfoam or use icofoam, or which fluid model you use. Then you have your transport properties and turbulence properties. In this case, interfoam requires by belows. In your solid, once again, we have mechanical properties, gravity, and our solid properties specifying which solid model to use. And then in our system settings, we just have your normal system settings as well. These are just the commands to run it and open it in PowerView, just for reference. These are some results you might get. Some comments on opening the case twice or using the extract block feature. Some extra FSI settings. So if we open up FSI properties, there's the 3 coupling methods implemented at the moment. So fixed relaxation, Atkins, accelerated relaxation, or just IQ, IMLS. So depending on which one you pick, they have some settings. So for example, you have to specify what the solid patch or fluid patch interface, FSI interface patch, or patches are. So they can be lists or individual patches. And then some settings for the coupling procedure itself. So some relaxation factors. Say some tolerances. So the way it works, it'll solve the fluid, then the solid, then the fluid, then the solid within each time step until that system converges. So you can specify how many outer correctors it performs and what tolerance, FSI tolerance it should run to. And then there's some other settings as well. So let me see, is that still running? Yeah, it's still running. Okay, so it must take 5 minutes then. So to run it, so if I refresh, we can see how far it's gone at the moment. Okay, so we're at that point now. So you can see the way it comes down, we'll hit the dam, performs it, and then this will start springing back and back, or it will start swinging back and forth. So because this is a fully elastic solid, it shouldn't dissipate energy apart from numerical or diffusion errors. But because the fluid's viscous in this case, eventually everything will stop moving because as the block springs back and forth, its energy, kinetic energy, will eventually be absorbed by the fluid itself as it comes to the setting. So can rupture be modeled? I never answered that. There is a test case, and there is a fracture test cases, simple fracture test cases. So I spent some time modeling fractures in OpenFOAM. For composites, it's pretty difficult, to be honest. There's a lot of convergence problems. I also spent some time in Texas, and the group there were using it to model fracking. So I see the group is still publishing and working on that code using OpenFOAM. So it is possible to model fracturing, and there is something called cracker FE mesh. So there is a tutorial in Solids4foam where it just takes a beam and it pulls it apart, and then the mesh splits in half. So you can actually model that. Okay, I will look. I can see there's more questions here, so I'm pretty much coming to a natural place to end this. You can see how many slides I have. So we have how many slides? 256 slides. So that's because this is kind of like a semi-documentation, just so you can come back to it and you can go through in your own time some of the extra settings. So in the first FSI test case, the beam in a cross-flow case, which I skipped over. I'll just show you what it looks like here. So it looks like this. This beam, and then there's incoming fluid, single phase, and then it just makes the plate oscillate back and forth. So if you want to go through that, it has some more information on FSI. But the primary motivation in Solids4foam was that any solid or fluid model implemented could be used with FSI. And so as soon as you implement a solid model, it's automatically available for FSI, is the idea, in principle anyway. Okay, so I'm going to just jump over to the questions now, because I realize we've only 5 minutes or so left. So let me see, the last one I asked, can rupture be modeled yet? And then, okay, so does the dynamic mesh belong to the standard OpenFOAM, or is it developed in Solids4foam? So there's different dynamic meshes here. So if we look at this case here, so when the solid starts moving, the fluid mesh has to move too. So automatically, we have a moving mesh fluid problem. So the underlying dynamic mesh for the fluid is just a built-in OpenFOAM. In this case, we're using velocity Laplacian or something like that. So that's just the built-in one. The only thing that's custom in Solids4foam is basically the boundary condition. So where we transfer the velocity of the solid to the fluid. So at the moment, that's actually done within the fluid-solid interface class. Though it's my plan that I would actually extract that into its own like point motion boundary condition to make it more independent. And then the solid models themselves, it depends on the formulation, but because they're Lagrangian, the mesh motion isn't independent. So once you just solve the equations, you automatically get the mesh motion. So you don't really have a mesh motion solved. Is morphing of mesh possible with OpenFOAM? So is morphing of the mesh possible? I can see Xiang, apologies if I pronounced your name wrong. So that's from you also. So maybe I've answered that already. I'm not sure. If I didn't, put another question in. When we use static mesh, does it mean that the solver assumes the deformation is very small and always solves the deformation at the original modes? Yes. Yes is the short answer for that. So if the deformation is small, that's a fine assumption. One comment is some of the nonlinear geometry solid models, they've hard-coded the mesh motion into the solver, so that you might see that static FE mesh is still used, but actually it's not really static FE mesh. It actually is moving the mesh, and you see the mesh is moved. So that's on my to-do list, is to like extract that code out and put it in a OpenFOAM format dynamic mesh, just to make it more clear. For the FSI case, if a floating plate is pushed down, can the buoyancy force be accounted for? So yes. So in this case, the only information that the solid sees from the fluid is a force. So it's basically just the force, whatever that force is. So it's two things, I guess, in fluids. It's the pressure force, and it is the viscous force, if a viscous force is present. So they're just transferred across, and then the solid will just move according to that. So of course, if you just have a floating block, you have to make sure the problem's well posed and the block doesn't float away. So actually, Liu Feng is probably a good guy to answer that if you want to chat to him afterwards. So he's done a lot of work on floating pieces of ice, And it really is that problem. So waves in the ice are driving the motion. So I'm sure he would be happy to talk about that with you. In your 5 minutes, that's fine. A few more questions. In your flexible dam break example, is the impact of buoyancy on the vibration of the solid accounted for? So I can see Hossein, you're asking this follow-up question. So it's in the interfoam or interfluid class, the only extra thing we have to define is define what the traction is or the force is on the on a given patch. So for that specific fluid model, its definition of force, we need that to be able to use FSI. So that gets implemented. So in this case, all the total, so you have pressure forces and you have viscous forces. So obviously interfoam is solving for dynamic pressure, but the total true force is due to the total pressure. So in this case, interfluid is passing the force due to the total pressure. So that includes buoyancy and viscous stresses. So hopefully that answers it. So yes, it does. And with your deformed mesh, does that artificially affect the phase field? So with the deformed mesh, does that artificially affect the phase field? So I assume you're referring to the phase field, you're referring to the volume of fluid field, like the alpha field. So does that affect it? So yes, when the fluid mesh moves, and then your underlying solver needs to be an ALE method, an arbitrary Lagrangian Eulerian. So if you look at the difference between interfoam and interdiam foam, you'll see there's some extra terms, and basically the convection term gets modified. And if you don't modify that, then you'll get very strange behavior. So yes, it does affect it, but the governing equations or the implementation of them changes to account for moving mesh. I'm not sure if I answered your question. That's like a general OpenFOAM question. So moving mesh versus non-moving mesh for fluid solvers. Yes, you have to account for that term. Is it working for large deformation? Yes. So I don't know if I showed it here, but it's not it. Yeah, so this was my presentation earlier today. So one project I've been involved in for quite a while now, 5 or 6 years, is with a metal forming project. And we use it there to really squash pieces of metal. So this is one simple example because I'm not allowed to show any of the cool, nice videos, which is really plain. But the cells really get squashed in this, so the deformation really is large. So these specific solver, a lot of the general code gets shared back into Solids4foam. The specific solver for this isn't, but the general methods in Solids4foam are there, so you can solve these style of problems. Thank you very much. I'm curious if it's possible to simulate the movement of an elastic body and a rigid body simultaneously, and how to choose. That's a good question. Not that the other questions aren't good questions, they're all good questions, but it's one that I have to think about. So, okay, a brute force way to do it would be just to set the stiffness. Your rigid body just set the stiffness to be a very large number, and it in effect will become a rigid body then. But that isn't maybe computationally efficient. So typically in OpenFOAM you use the 6 degree of freedom solver to do rigid body. So you could have 2 different parts and use a 6-DOF fluid solver, and then for your elastic part, use like Solids4foam or a similar solver. You may require some coding, I'm guessing. If someone hasn't done something like this before in OpenFOAM, my experience is you may have to get stuck into the code to connect the features yourself. Okay, so it's 4 o'clock now. I can see there's one more question in the chat. Danielle, feel free to stop me because I don't want to run over time. But the final question was, I wonder, is Solids4foam compatible with Overset? Yes, so Overset is available in the Foam Extend 4.1 version. So there is Overset, is it ICO, Overset Foam, or whatever it's called. A port of that is available in Foam Extend 4.1, at least in the Solids4foam when you compile it with Foam Extend 4.1. I haven't played it too much, but in my experience, there's challenges with Overset, as with all of these things. So have a go and play with it. Okay, thank you very much for everyone's time.